Okay, so welcome back. Now we're going to see the first part of molecular genetics. That part is called replication, as I explained in the first video. Okay, so molecular genetics, part 2 actually, because part 1 was the review, and it's going to be called replication. Replication is the process by which we're going to get more DNA. Okay, so brace yourselves because this is going to be a little bit difficult. Okay, we start obviously in step 1. In step 1, we're going to have a DNA double helix like this. Okay, now the important part of DNA is not the double helix in itself, but it's the information that it contains, the genes. And if you remember, the genes, okay, are inside the DNA. If the genes are inside the DNA, okay, inside the DNA double helix, what do we have to do? We have to open the DNA double helix. How do we open it? With something that we call enzymes. Enzymes are proteins, okay, that have a function. What function? Whatever they do, okay? So first we're going to open the DNA, okay, with an enzyme that we're going to call HELICASE, okay? And we're going to represent like that with an 8, okay? And this is HELICASE, okay? So HELICASE is going to recognize a bit of DNA, okay? You don't need to know where and how or why, but it is going to recognize a bit of DNA, okay? And it's going to open it like this. So we have our DNA double helix, okay? And then helicase is going to come and open. Forgive me if I'm silent when drawing, but this video needs a lot of drawing, and I will try to cut most of the drawing parts out, but in some cases it's just necessary to be here because I need to start explaining things. So helicase, as you've seen from this, this is going to be a sequence. I'm going to try to represent most of the things so you can see them, how it moves and everything, but eventually we're going to move to this side, so just have a little bit of imagination. Yes, so helicase has come and opened a little bit of DNA, okay, this little bit here, so helicase has opened it, and we're going to have lots of nucleotides here. What I'm representing with these little sticks are, you guessed right, the nitrogen bases, okay? So those little sticks are the nitrogen bases that we have to breed and replicate. How do we do that? Okay, with an enzyme that is called the DNA polymerase. But first we have to, okay, the normal state of DNA is this DNA double helix. So it will try to revert itself to the DNA double helix even if we're opening it, okay? So when the helicase opens it that way, like this, okay, it's going to try and close itself as soon as possible. To prevent that, we're going to use these little green dots here that are going to attach, that are called topoisomerase. Topoisomerase. Topo place, iso the same. So they're trying to keep that place as they found it. Okay, topoisomerase, those little green dots. Okay, so the topoisomerases are going to keep the DNA open as the helicase opens it. we're going to use an enzyme that is called the DNA polymerase. Okay, DNA polymerase is going to be represented like this. Okay, DNA polymerase. DNA polymerase can only add a nucleotide if there's a nucleotide. Okay, so and the DNA polymerase is going to add nucleotides in a 5' to 3' direction. Okay, so it's only going to add nucleotides in that direction. Okay, so we're going to have a problem. If it can only add nucleotides to other nucleotides, and now here we have these strands of DNA, remember, they are called strands of DNA. Okay, the original strands of DNA. Okay, and we need to make another strand in order to replicate the DNA. How does it work? We need to use something that is called a primer. So a primer is a random sequence of nucleotides. Sorry, I'm not going to use this color because you cannot see it. I'm going to use I'm going to use this one. Yes, different enough. So the primer, okay, this is called a primer, works as the primary in makeup. For example, it's the base upon which you will construct the rest of the makeup. In this case, the primer is the base upon which you will build the rest of the DNA strand. Okay, so the DNA polymerase comes here, recognizes the primer, okay, and starts building the new DNA strand like this. Okay, in this direction, adding nucleotides, but okay, in this direction, adding nucleotides in a 5' to 3' direction. So in this case, 5' is going to be here, okay, and 3' is going to be here, and the direction of growth is going to be like that. Okay, as DNA strands are complementary, anti-parallel, 5' for the original sequence is going to be here, and 3' is going to be here. Okay, so you see, anti-parallel. That means that in this other original strand, this is going to be 5', here is going to be 3', and we're going to have that direction. What happens at the top? Okay, we have to replicate the strand the other way. Okay, so here we put the primer, and then the DNA polymerase will start working, okay, and put a chain 5 to 3. You see, we have always complementary strands. Now, what happens? That we have to continue replicating all these fragments, okay? So step 3, the helicase is going to move a little bit more. This is our DNA strand. Here. The helicase is going to move, or in this case, a lot. More DNA is going to open. As you can see, we've opened a great more deal of DNA because the helicase has moved in that direction. Yes? So it's going to move a lot. Now, things that we had in the previous drawing, okay? we had a primer here, and we had another primer more or less here. Okay, we had the polymerase that had replicated all this part here, and it's now over here. The polymerase works as a sort of as a snail, okay? That it's going to just move around, and it's going to pick the complementary nitrogen bases and put them where they have to be put, okay? Thus creating the new strand, okay? The new strand that is 5 to 3. But here there is no more DNA, so the DNA polymerase is not going to find anything to replicate, okay? So this will be the end of this strand. Down, okay, we have this DNA polymerase that is going to replicate the strand all over the place, and it's going to continue replicating because as the helicase moves, this strand can move and put more and 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 more nucleotides. Sorry, I erased the primer with my clumsy little finger. Okay, so you've seen now what the problem is here, okay? Here the problem is that one strand can keep on going forever until the molecule ends, okay? And the other strand has to begin again, yes? So we're going to put another primer, okay? And another DNA polymerase is going to come and work in a 5' to 3' direction. Yes? What happens when this new DNA polymerase here, the second one, finds the primer? It's going to happen the same that if you're poking with your mobile phone and you find a lamppost, okay, you're going to fall. Okay, you're going to hit yourself with the lamppost and then you're going to fall. So the DNA polymerase and the primers are basically the same. Okay. Now, the problem is that as the helicase moves, okay, it's going to open more DNA, and in the top strand here, okay, in this drawing, okay, the original strand, remember, was 5' to 3' in this direction, and this is 5 to 3 in this other direction, okay, and this top strand is going to be replicated in fragments, okay, and the bottom one is going to be replicated continuously, okay. So the strand that is replicated continuously, okay, we call it the leading strand, okay, and the strand that is replicated by fragments is going to be called the lagging strand, okay, leading and lagging strand. As you've seen, the lagging strand is called like that because it's going to take a little bit more time in order to be fully replicated, okay. It's going to be slower than normal, okay, and if you're slower than normal, you have some lag, okay, as in video games. So we're going to go to step number 4. In step number 4, the DNA is going to be fully opened, okay? What is going to happen? We're going to have the helicase joining a little bit of both strands, like this. we're going to have in the leading strand, okay, the leading strand is going to be fully replicated like this. But the lagging strand is going to be replicated in fragments. The process will have had to start it several times by now. Now this one is not going to have anymore the DNA polymerase. This one just fell off. I'm going to put DNA polymerase here, fallen off. And this one is still in process. Okay, like this. So as you've seen, there's the leading strand that has already finished replicating, okay? And the lagging strand that is still working. Okay? Now, remember that the lagging strand has a direction of 5 to 3, and the leading strand has a direction of 5 to 3 here. So leading and lagging. Okay? Now, the ligase, as you see here, okay, is going to take out the primers, okay, take out the primers and join this little gap that you see here, okay. So once it works, once the ligase starts working, okay, the DNA can coil again, okay. So the topoisomerases are going to fall off. It's going to coil progressively, but it cannot work if there's a DNA polymerase here, okay, or here. So it's going to take a little bit more time to finish in the lagging strand. As you can see, the lagging strand is going to finish a little bit later than the leading strand. Okay, that's why it's called lagging strand, because it's going to lag a little bit more than the leading strand. Okay, then you can see that when this one is completely finished and all the topoisomerases have fall off, this one is still in the process of coiling and everything. Okay, now, and if you take an important thing out of here, okay, is that the DNA replication is semi-conservative. Semi-conservative means that it's going to conserve, sort of, have the old information, have the old DNA molecule. Okay, you're going to have half old and half new. Okay, half black and half blue, as you can see here. So half and half. Remember, that is super important to remember. Okay, because we're going to use it a little bit more. Normally, when we talk about mutations and everything, you're going to see why this part is important. Okay, so half and the new molecule of DNA is going to be replicated by the DNA polymerase, and the other half is going to be the old one, okay, the template one that we've used. Okay, so things that we've seen is that the helicase opens the DNA strand, okay, then the topoisomerases, the green dots, keep it open, so the DNA polymerase can work, okay. The DNA polymerase, remember, that can only add nucleotides to another nucleotides and works in a 5' to 3' direction. So it needs a primer to start working. Once it gets a primer, it can replicate the new DNA strand, okay? That is going to be complementary to the old DNA strand. Remember, A, T, C, and G, as we've seen in the review video. Then, when the helicase opens a little bit more, then the leading strand can be replicated completely because it has a 5' to 3' in the direction of the helicase opening, but the other is going to have a little bit more difficulty, okay? It's going to be replicated in fragments. These fragments have a name, okay? These fragments are called Okazaki fragments, okay? I need to write it here. Okazaki fragments, okay? Those are going to be Okazaki fragments. How many Okazaki fragments can there be in a DNA molecule? Well, thousands of them, okay? Because DNA molecules are really, 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 really long. Here we have only 3, 1, 2, and 3. But the Okazaki fragments can be thousands of them, okay? Then the ligase is going to take out the primer and join the gap between the primer and the new DNA. Primers are random sequences of nucleotides, okay, that will fit there. So they have to be taken out to prevent mutations. So the ligase is going to take them out and join the gaps. So it's going to work only once in the leading strand and several times in the lagging strand. That's why when the leading strand is already coiling, the lagging strand is going to be working with ligases and blah blah, and that the DNA replication is semi-conservative. Okay, so that's it for this video. Try to watch it as many times as you can, and then ask me in class. Okay, I hope that you've enjoyed it. See you in school, and take all the notes that you want. Hear me several times because you're not seeing me. Hello, you're not seeing me, really. And I hope that you enjoyed it, understood it, and that's it. Hello and goodbye.